Hi everyone, I am John Paul Del Mundo Arcilia, a first year student of Bachelor of Science Chemical Engineering and Chemistry at Mapua University. So for today, I will be discussing two problems from the book of Skoog and West, Fundamentals of Analytical Chemistry 9th edition. The problems that I have chosen are problem 7-6 and problem 10-12. The problem 7-6 it's all about the determining whether a datum is an outlier using a Q-test, and the problem 10-12 is all about finding the concentration solubility product constant. For the problem 7-6, the last result in each set of data in problem 7-4 may be an outlier. Apply the Q-test 95% confidence level to determine whether or not there is a statistical basis to reject the result. So beside the problem is the set of data obtained from problem 7-4. So basically the problem tells us to determine whether this, 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 and this are outliers for a given set of data. So before we proceed to the computation of the problem, let me give you a little background for Q-test, or what a Q-test is. So a Q-test is a statistical measure that will help us to decide whether to retain or discard a questionable datum. So why it is important for us to know the Q-test? For example, you conducted an experiment and you recorded set of measurements. There is this one measurement that differs from others, or are so deviated from other set of measurements, and you want it to be removed, but you cannot remove it easily, or you cannot just simply remove it. You have to apply statistical measure, which is basically the Q-test. So the Q-test is the Q calculated is equals to gap over the range. The gap is the questionable value minus the nearest value in it all over the highest value minus the lowest value. If happened that the Q calculated is greater than the Q table, the questionable point should be discarded. So to obtain the value for critical value, or the Q table, we will be utilizing this table of values for Q for rejecting the data. This is the number of data in a set, and this is the degree of freedom. Since we will be using 95% confidence level, we will be using 0.05 as our degree of freedom. For example, we have 5 recorded measurements or 5 recorded data from a set. Then we will be using 0.710 as our Q table. So since you have a little background about the Q test, we will now proceed to the problems. So now we will proceed to the calculation, and for the set A, the questionable value is 3.2, and from the table we will obtain 0.710 as the questionable point or the critical value. Just this one. So from the calculation, the absolute value 3.2, which is the questionable value, minus 3.0, which is the nearest value to 3.2, all over 3.2, which is also the highest value, minus 2.6, which is the lowest value, we will obtain 0.33 as the Q calculated. And 0.33 is less than 0.710, therefore, Q calculated is less than the Q table, meaning to say the questionable point is not an outlier. Therefore, we will retain it, or we will keep it. So why it is important for us to know whether the questionable point will be going to kept or will be going to be rejected? It is because it has something to do with the computation of the standard deviation. It happened that the questionable point is an outlier, then we will not going to include it to the computation of the standard deviation. And if you not include it to the computation of standard deviation, the standard deviation will be smaller than the standard deviation when we include the outlier. And smaller standard deviation means that the set of measurements is precise. I hope I made it clear. So for the second set, or for the set B, the questionable value is 0.472. And from the table, we will obtain 0.710 again as Q table or the critical value since we have 5 data in a set. So from the calculation, we will obtain 0.33 as the Q calculated, and 0.33 is less than again with 0.710, meaning to say that the Q calculated is less than the Q table. The questionable point is again not an outlier, and therefore we will retain it or we will keep it. For the set C, the questionable point is 70.10, and from the table we will obtain 0.970 as a critical value since we only have three data in a set. And from the calculation, we will obtain 0.86 as the Q calculated. And 0.86 is again less than to 0.970. So therefore, Q calculated is less than to Q table. So meaning to say that questionable point is again not an outlier. Therefore, we will keep it or we will retain it. For the set D, the questionable point is 2.5, and again our Q table or the critical value is 0.710. And from the calculation, we will obtain Q calculated as 0.60. Since 0.60 is again less than to 0.710, the Q calculated is less than Q table, which means that the questionable point or the 3.5 is again not an outlier, and we will retain or keep it again. For the set E, the questionable point is 0.900, and from the table we will obtain 0.829 as the Q table or the critical value since we only have 4 numbers of data in a set. And from the calculation, we will obtain 0.815 the as the Q calculated, and since it is less than again with or less than to 0.29829 rather, therefore the Q calculated is less than Q table. The questionable point is again not an outlier, therefore we will keep or retain it. But for this set F, the questionable point is 70.21. From the table, we will obtain 0.829 again since we have 4 data in a set. And from the calculation, we will obtain 0.9545 as Q calculated. And since now this is greater than to the Q table, the questionable point is an outlier. Therefore, we will discard it. So meaning this will not be included, or we will not be including it to the computation of standard deviation. So that's it for the 7-6 problem. Now we will proceed. So for the problem 10-2, we will now be calculating the concentration solubility product constant, which is from the lesson effect of the electrolytes in chemical equilibria. So for this problem, for a solution in which the ionic strength is equals to 8.0 times 10 to the negative 2, calculate the concentration solubility product constant for letter A, silver thiocyanate, lead iodide, lanthanum iodate, and magnesium ammonium phosphate. So basically this problem tells us to calculate the solubility or the concentration solubility product constant, or the Ksp prime. So before we proceed to the calculation, I'll just be giving you some the 2 equations used for the calculation of the Ksp prime. So to determine the values of Ksp prime or the concentration solubility product constant, we will be utilizing these 2 equation. First is the Ksp prime is equals to Ksp all over the activity coefficients of x and y, where Ksp is the solubility product or the thermodynamic equilibrium constant. Gamma is used to denote the activity coefficient of the ions and the species, and the Ksp prime is the solubility product constant. To know the value of these and these, we will be using the Debye-Huckel equation if it is not given. So the Debye-Huckel equation is an equation that permits us to calculate the activity coefficients of the ions. It is negative logarithm of the activity coefficient equals 0.51 times the charge times the square of the charge multiplied by the square root of the ionic strength all over 1 plus 33 times the effective diameter multiplied again by the uh, ionic strength, where the gamma x is the activity coefficient of the first species or any other species or the ion, and z is the charge of the ion, and mu is the ionic strength of the solution, and alpha x is the effective diameter of the hydrated ion x in nanometers. And the effective diameter, or the alpha x, will be obtained using this table, the activity coefficients for ions at 25 degrees Celsius. These are the ions, and this is the effective diameter of each ions. For example, we will be using a lithium ion, then we will be having 0.6 as the effective coefficient. So now let's proceed to the actual computation of the KSP prime, since we have already known the two equations that we'll be going to utilize. So first, for the silver thiocyanate, the ions are silver ion and thiocyanate an ion. The charge of silver ion is positive 1, and the effective diameter of silver ion is 0.25. Substituting it from the equation, negative logarithm of the activity coefficient of the silver ion is equal to 0.51 times the charge of the ion, which is 1 square, multiplied by the square root of the ionic strength, which is the 8.0 times 10 to the negative 2, all over 1 plus 3.3, multiplied by the effective diameter 0.25 times 8.0 times the square root of 8.0 times 10 to the negative 2. From the calculation, we will obtain 0.7368 as the activity coefficient of the silver ion. For the thiocyanate ion, the effective diameter of is 0.35, and the charge is negative 1. So substituting it to the equation, negative logarithm of thiocyanate, the coefficient of thiocyanate ion is equals to 0.51 times 1 squared multiplied by the square root of ionic strength, which is again the 8.0 times 10 to the negative 2, all over 1 plus 3.3 times the effective diameter of 3.35, and the square root of 8 times 0 times 10 to the negative 2, which is the ionic strength. Again, we will be obtaining 0.7780 as the activity coefficient of the silver thiocyanate. By the way, 0.51 and 3.33 are constant values. So to determine the solubility product constant, or the KSP prime, since we have KSP equals to 1.03 times 10 to the negative 12, the concentration solubility product will be equal to 1.03 times 10 to the negative 12 all over the activity coefficients of the ions, which is the activity coefficients of silver ion and the activity coefficient of uh, the silver cyanate, which is 0.7780. From the computation, we will obtain 1.8 times 10 to the negative 12 as the KSP prime. So now let's proceed to lead iodide. The ions are lead ion and iodine an ion. The effective diameter of lead ion is 0.45, and its charge is positive 2. So substituting it to the equation, we will obtain 0.3923 as the activity coefficient of lead ion. For the an ion, the 0.3 is its effective diameter and its charge is negative 1. So again, substituting it to the equation, or to the Debye-Huckel equation, we'll obtain 0.7714 as the activity coefficient of the iodine an ion. So to determine the KSP prime, the KSP for this solution is 7.9 times 10 to the negative 9. So 7.9 times 10 to the negative 9 all over the activity coefficients of ions, which are 0.3923 multiplied by 0.7714 squared. It has squared it because of this coefficient. Is equals to 3.38 times 10 to the negative 8. This is the KSP prime, or the concentration solubility product constant of the lead iodide. Next, we will proceed to the third, which is the lanthanum iodate. The ions are lanthanum and iodate, an ion. For the lanthanum ion, the charge is 3 positive and the effective diameter is 0.9 rather. Then substituting it to the equation, substituting those values to the equation of the Debye-Huckel equation, we'll obtain 0.1968 as our effective coefficient of lanthanide ion. And the effect, and for the iodate anion, the effective diameter is 0.4 rather to 0.45, and its charge is basically -1. Substituting it to the equation, we'll obtain 0.7952 as the activity coefficient of the iodate ion. And to determine the KSP prime, we have 0.1 or 1.0 rather times 10 to negative 11 as its KSP, or the solubility product, or the thermodynamic equilibrium constant, divided by the activity coefficients of lanthanum ion and the iodate anion is so 1.0 times 10 to the negative 11 all over the 0.1968 times the 0.7952 cube. It has its cube because of this 3 iodate anion. It will be equal to 1.1 times 10 to the negative 10. So 1.1 times 10 to the negative 10 is our KSP prime for the lanthanide or lanthanum iodate. So for the last solution, which is the magnesium ammonium phosphate, the ions are 3, which are the magnesium ion, ammonium ion, and phosphate anion. For the magnesium ion, the charge is positive 2 and the effective diameter is 0.8. Substituting those values to the equation, we'll be obtaining 0.467 as the activity coefficient of the magnesium ion. And for the ammonium ion, the effective diameter is 0.25 and its charge is positive 1. Substituting it to the equation, we will be obtaining 0.7638 as the activity coefficient of the ammonium phosphate. And lastly, for phosphate ion, the charge is -3 and the coefficient, or the effective diameter, is 0.4. Substituting those values to the Debye-Huckel equation, which is 0.51 times 3 squared times the square root of 8.0 times 10 to the negative 2 plus all over 1 plus 3.3 times the 0.4, which is the effective diameter, multiplied by the ionic strength, which is 8.0 times 10 to the negative 2, we will be obtaining 0.1334 as the effective coefficient of the phosphate ion. So to solve the KSP prime, or the concentration solubility product constant, we will be using KSP. There is a correction in this. The KSP for the magnesium ammonium phosphate is 3.0 times 10 to the negative 13 rather than 1.0 times 10 to the negative 11. I think that's from the KSP of the lanthanum iodate. So 3.0 times 10 to the negative 13 is all over the activity coefficients of magnesium ion, ammonium ion, and phosphate ion, which are 0.467 times 0.7638 and 0.1134, will be having 7.14 times 10 to the negative 12 for the KSP prime, or the solubility product constant. So that's it for the video. I guess you learned something, and if you have questions or if you have corrections, please feel free to comment to the suggestion box or the comment section or the comment box. Thank you.